the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are going through linear transformations, specifically a topic called the matrix of a linear transformation. This entire series of videos within this topic, they're dedicated to finding the matrix for a linear transformation, but within this topic, we really need to delve into the idea of the functional representation of a transformation. That is, what are the main differences between functions and transformations? Because there are actually differences. I had made mention that a lot of people think of transformations as functions, but there are some significant differences. And so this video is dedicated to opening that conversation up. There are two major features about transformations that we need to talk about: onto mappings and one-to-one mappings. So this video is just dedicated to onto mappings. A mapping T, and remember, mapping is just another word for transformation. So a mapping T from Rn to Rm is said to be onto Rm if each vector in Rm is the image of at least one vector in Rn. And as a clarification, therefore a mapping is onto if the range of the mapping is equivalent to the codomain of the mapping. And remember, we had this conversation in a previous video about the difference between the range of a mapping and the codomain of a mapping. This image should help out. If you take a look at this image right here, you have the domain of your transformation. You have all those elements from your domain that get plugged into your transformation, and then their images get mapped to some subset of your actual codomain. Remember, the transformation itself maps Rn to Rm, but nobody ever told you that it maps Rn to everything in Rm. And I made a big point of that when I introduced the idea of the range and the codomain of a transformation. The reality is, the range of a transformation, which is a set of all outputs of the transformation, could be a subset of the codomain Rm. It doesn't have to be the entire Rm. And if it's not the entire Rm, it's not onto Rm. That's a good way of thinking about it. If your transformation does not cover all of Rm, then it doesn't transform things onto all of Rm. It's not onto Rm. Versus this image right here, and I shouldn't say image, I should say this figure right here, because image is very special in linear algebra. But this figure shows us that the domain of our transformation, which is right here, maps completely over to the range over here, which is all of Rm. That's what this picture really means, is that the box that normally is there for Rm is actually the range as well. So because the range and the codomain are the same, T is considered onto. It maps everything onto Rm. So I think that visual is very nice. Now, as a concept here, the concept of onto, the range and the codomain being the same, is actually considered an existence concept because it couples with the question, does there exist a solution to T of x is equal to b? If the transformation maps onto Rm, then every vector in Rm is from a transformation of a vector in Rn. That is, if you randomly pick some vector in Rm, because everything in Rm gets mapped to from Rn, there must exist a vector in Rn that gets mapped to that vector b. So it answers the existence question. Hey, if I hand you a random b, is there a vector x that I would plug in the transformation to get b, transformation of x equaling b? And the answer is yes. If it's onto, absolutely. Everything in the codomain is within the range of the transformation. So let's use an example to express this. Let T be the linear transformation with standard matrix A, which you see right here. Does T, the transformation, map R5 onto R4? That is, if B is a vector in R4 and is arbitrary, can we guarantee there is an X in R5 such that T of X is equal to that B? Well, T of X is equal to AX by definition because we've been told A is the standard matrix for the transformation. So whenever you see T of X, you're really looking at A times X, that A being the matrix that we see up above. So we're essentially asking, is there always a solution to AX equals B? Now I'm going to write this in an augmented matrix just to show something. Notice when I write this in an augmented matrix, we have a pivot in each row of the coefficient matrix. And to remind you, we have a theorem that says something about this. Now, the theorem lists that you should keep at hand, at least when you're working through homework or when you're reading through the text, is incredibly important. And this is why I give my students that every section that we go through, they have a growing list of critical theorems. And here you can see some of those theorems right here. It's a very long list, but really the ones you kind of pay attention the most to are the numbered theorems, the theorems that start with theorem number whatever. That theorem 0 is actually not part of the textbook that I use, but I include it because that theorem 0 is all about homogeneous matrix equations, which is not what we're dealing with. But on we go. Theorem 1, theorem 2, theorem 3, theorem 4. That theorem 4, though, is the one I'm interested in. All of the statements in that theorem 4 are equivalent statements. That is, either they're all true or they're all false simultaneously. And that very last statement within theorem 4 states that A, the coefficient matrix, has a pivot in every row. Then, if that's true, 1, 2, and 3 are also true. Specifically, 1. For every vector B in our codomain, AX equals B has a solution. So we're going to use that here because really we were asking that. If B is arbitrary, does AX equals B have a solution? So therefore we know that no matter what B is, because we have a pivot in each row, AX equals B will have a solution. Now to cite that is very, very important. So let's go ahead and fix the wording to where it's satisfactory. Since A, which is a coefficient matrix, has a pivot in each row, AX equals B has a solution for each vector B in Rm, and that is true by theorem 4. Hence, by definition, T maps R5 onto R4. Notice how I buttoned that up. I made sure that it really was clean, clear logic. It also reinforces the idea of onto, the fact that a mapping is onto if you can grab any vector from the codomain and it is the result or the image of a transformation of a vector from the domain. There's not much else I need to say about onto mappings. It's just important that we start that conversation now. If you're following my videos in the order that I produce them, the next video will be one-to-one mappings. All right, I hope you guys have a great day. I hope this video was helpful for you, and be good humans.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.